In this problem, we need to find the dimensions that will give a metal storage tank with volume 1 cubic meter in the shape of a right circular cylinder surmounted by a hemisphere. Now here the point is that we need to minimize the surface. We want to use the least amount of metal. So it has it's a cylinder. There we go. And then it's surmounted by a hemisphere. So it has half a sphere on top. And this shape has two important features. One is the height of the cylinder. The other one is the radius of the sphere. So those are the two we need to work with. And then there are two quantities here, the volume and the surface area. Now the volume is probably the easiest of the two. We just need to add together the volume of the cylinder, which is the volume of the base, pi r squared times the height, okay, plus the volume of the hemisphere. So here we have remember the formula for the volume of a sphere, 4/3 of pi r to the power 3, but it's a hemisphere, so we need to take just half of it. Okay, here let me make a note. For a sphere of radius r, the volume is 4/3 of pi r to the power 3, and the surface area is 4 pi r squared. Okay, these are things we need to know. So I was saying the surface area in the case of this recipient, this tank. Now we need to look carefully what is the surface area. So it has three pieces, three walls. One is the bottom, then there is the proper wall of the cylinder, and then there is the top part that is the surface of the hemisphere. Okay, so we need to add together all those three. So the bottom part is just pi r squared it's just the area of the bottom circle plus, and then the wall is, if you unfold it, you will see that it's a rectangle, right? It's a rectangle that has length 2 pi r, which is the length of the rim. Okay, 2 pi r times times the height. Okay, because it's a rectangle. So this is the wall. Let me move this over here. And then the last part is the top, the dome. In this case is 4 pi r squared. That's the surface area of a sphere, but then divide by 2. All right, and then we see 2 pi divided by 2 makes, 4 pi divided by 2 makes 2 pi. So 2 pi r squared plus pi r squared, we can write it together. This is 3 pi r squared plus 2 pi r h. Now the problem also says Here, if you notice, we have a bit of a problem. We have two variables, okay, and we want to optimize the surface. So we need to get rid of one of the two. But I was saying the problem also says that the volume equals 1 cubic meter. Okay, we have it here, the formula. So we can use this formula to solve for h. I'm going to simplify this here and just write 2 instead of 4 divided by 2. Okay, so here, let's solve for h. So h equals 1 minus 2/3 of pi r squared divided by pi r squared. No, in the numerator is pi r to the power 3, the cube. Okay, so we can write this a little better. 1 over pi r squared minus 2/3 of r, so 2r over 3. Here, in this problem, it's important to try to simplify at every step, because otherwise the computation gets very out of control. Okay. All right, so then the surface area, which we know it's 3 pi r squared plus 2 pi r h. Here I can plug in the formula I just found for h. And now again, let's simplify, because if we take the derivative of this, it's going to be complicated. So this is 3 pi r squared plus 2 divided by r minus 4 pi r squared divided by 3. Okay, and we have r squared in the first and third terms. So we can write 3 pi, well, actually 3 minus 4/3 pi r squared plus 2 divided by r. And this is 9 minus 4, 5/3, so 5 pi thirds r squared plus 2 divided by r. And this is s. Okay, so we can take the derivative. The derivative is going to be 10 pi thirds r minus 2 divided by r squared. The derivative of 1 over r is minus 1 over r squared. And we are almost there. Now we want this to be equal to 0 and solve for r. So that means 10 pi over 3 r equals 2 over r squared. So we can actually write a cube. Okay, and this is a 2. Then I can simplify the 2 and get r to the power 3 equals 3 divided by 5 pi, and then just take the cubic root, and that's it. That's r. And we need to check that it's this is a minimum. Okay, so just for that we do a sign chart. We are interested only in r that is positive, so we go from 0 onwards. And here, with a computation just like this one we did, what we find is that the derivative is negative on the left of 3 divided by 5 pi to the power 1/3, and then it's positive, always positive. Okay, so from 0 it decreases, and then it's ever increasing. So that means that this is not only a local minimum, but also an absolute minimum. Okay, because the function after that is always increasing. So if it doesn't go down again, it cannot have another minimum. All right, so that shows that what we found is an absolute minimum. The only thing that is left, because they are asking for the dimensions, is to write down what is h. So h, yeah, here. Well, there are several ways in which we can do this computation. 1 minus 2 pi r to the power 3 divided by 3 pi r squared. No, this is 3. There we go. So 3 minus 2 pi r to the power 3 divided by 3 pi r squared. Here we plug in what we got. So this is 3 minus 2 pi times r to the power 3 to the 1/3 makes 3 divided by 5 pi divided by 3 pi, 3 divided by 5 pi to the power 2/3. All right, and this is 15 minus 6 divided by 5. So let me write it like this: 15 pi, 3 divided by 5 pi to the power 2/3. And I'm going to simplify until the end so that we see there is a bit of a funny thing in the end. So this is 9 divided by 15 pi, 3 over 5 pi to the 2/3. Actually, well, let's do one thing at a time. I can simplify. So this is 5, this is 3. So 3 divided by 5 pi, right? But then I have 5 pi here dividing. There we go. So I get 3 to the 1/3 divided by 5 pi to the 1/3, which, if we look at the expression for r, is exactly equal to r. So this is what I wanted to show you. Actually, the one that gives the minimum surface is going to be the one that has the same height as radius for the hemisphere, for the dome.